Okay, so we're going to continue on looking at the derivatives of log functions, and we're going to do a little bit more with derivatives of exponential functions as well. So we'll start off with the e bases, right? So we'll look at the natural log function. In this case, the derivative of the natural log is 1 over x. It's a pretty straightforward derivative, and x is bigger than 0. And so if you chain rule this, if you had a function inside the log, you would go 1 over u times du dx, and then your u would have to be greater than 0. So that's your derivative of the natural log. An example of this would be, let's take the derivative of natural log of, let's do x squared. So I would take 1 over x squared, so f prime would be 1 over x squared, times the derivative of x squared, which is 2x. So I get 2x divided by x squared, and I can simplify that to 2 over x. The other thing we want to do with derivatives is, what if the base is an e? Because we've looked at a bunch of derivatives here where the base is e. We've done the derivative of e to the x, we've done the derivative of natural log of x, but what about if it's 2 to the x, or 3 to the x, or log base 5 of x? So those are also derivatives we want to know how to take. So let's look at how to find those derivatives. So if we have, for exponentials, a to the x, so this could be any base. Let's imagine what's happening with e to the x, right? So with e to the x, we just get e to the x. So with a to the x, we should just get a to the x back. But e has a special property. Really what's happening here is we're doing the same exponential function, and then we're multiplying it to the natural log of that base. In this case, when I do the natural log of e, that's just 1, so it goes away, we just get e to the x. For any other base that isn't e, it's not going to equal 1, and so we need to multiply that natural log on there. And the same rule applies for when it's a chain rule, you'd have to multiply in that chain rule bit as well. So if you had d dx of a to the u, you go a to the u times natural log of a times du dx. Similarly, for logs with different bases that aren't natural log, think of it like a scaling, right? So if we have log base a of x, it's still the 1 over x bit from the natural log, but we're going to scale that by the natural log of the base as well. So we're multiplying 1 over natural log of a. And then same with the chain rule, you'd have to multiply on the derivative of that inside function. So let's do some examples with this. So I have natural log of 2x. I want to find its derivative with respect to x. So natural log of 2x, that's 1 over 2x, times the derivative of the 2x, which is 2. So I get 2 over 2x, which is just 1 over x. In this case, actually, the scaling of the inside of the log doesn't really change the rate of growth of it. It's still, the rate of growth is still 1 over x. Next one, we have natural log of x cubed. And so let's write this like this. Natural log of x cubed, or this could be written as natural log cubed x. So for finding this derivative, here the outside function is the cubing. So we're going to deal with that first. It's going to be 3 natural log squared of x. And then we take the derivative of natural log of x, which is 1 over x. So we get 3 natural log squared of x over x. For the next one, we have a base that isn't e. We have log base 2. We want to find its derivative with respect to x. So we do 1 over the inside bit. So we keep that the same. And then we take the derivative of the inside piece. So that's times 2x. And then we multiply 1 over natural log of that base, natural log of 2. And so that's our full derivative expression. So we get 2x divided by natural log of 2 times x squared plus 1. The last one, again, here we have an exponential function with a different base. So we deal with it as if it was e to the x. So we repeat it take the derivative of the inside, and then scale it by the natural log of the base. So you get 3 natural log of 2 times 2 to the 3x. Hopefully that should still feel pretty straightforward to find derivatives. We're just using these different derivative bases, but the same rules from before. The last thing we're going to do in this is something called logarithmic differentiation. So logarithmic differentiation is a process that we can use to find some derivatives of more complicated functions without needing the product rule or the chain or the quotient rule. So before we get to the steps, let's just look at this function. Y equals x times square root x squared plus 1. I could take this derivative using the product rule and the chain rule. Right? I can do dy dx equals derivative of x is 1 times square root x squared plus 1 plus 1 plus x times 1/2 x squared plus 1 to the negative 1/2 times 2x. And I could simplify that down, work through it, and find my derivative. That's fine, it would work. I would get a very complicated expression. And it gets even more complicated if I have a quotient like this with a bunch of chain rule things to do as well. So while these are possible and these are problems you've had before, we can use logs to make this process a little simpler. So let's look at this process. So if we have y equals some function, what we're going to first do is take the natural log of both sides. So we'll get natural log of y equals natural log of u. Then we're going to use log properties to get rid of as many products, quotients, and exponents as we can. This is key. This is why we go over log properties in terms of calculus, is it helps us simplify a lot of functions when we're taking derivatives of them or taking integrals. So because of products, quotients, and exponents can go away with logs, because products can become addition, quotients can become subtraction, exponents can become multiplication. So we can simplify those functions a lot using log properties. Once we do that, then we're going to differentiate everything. So natural log of y would become 1 over y times dy dx. Oh, we'll do y prime since we don't know it's an x. Times y prime, and we'll get 1 over u times u prime. And then we can move the y to the other side to solve for dy dx. And then lastly, substitute for y and simplify it. So then we'll substitute u in for y, and we can simplify it. And in the end, we'll just get what u prime is. So let's go through this process on this problem. So the first thing we're going to do is take the natural log on both sides. So the natural log of y equals natural log of x times x squared square root x squared plus 1. Now I'm going to use log properties to get rid of the products on the right side. So instead of natural log of x times x squared plus 1, I'm going to do natural log of x plus natural log of square root x squared plus 1. And I can simplify that even more because x squared plus 1 and its square root is x squared plus 1 to the 1/2. So I can make that 1/2 natural log x squared plus 1. So now I've gotten rid of the exponents, I've gotten rid of the product. It's a much simpler function to take derivatives of. So now I'm going to differentiate implicitly. So I get 1 over y times dy dx equals 1 over x plus 1/2 times 1 over x squared plus 1 times 2x. So the 2's can cancel here. I'm going to multiply the y to the right side. So I get y times 1 over x plus x over x squared plus 1. And then I resubstitute y back in. And I get my derivative on this. So a much faster way sometimes to find these derivatives. And then you can also simplify the fraction on the inside, so we can do a little bit more work with it and eventually get something that's way simpler to look at as well. Let's look at this next one. So this one is x minus 2 squared divided by square root x squared plus 1. So this is a quotient rule. But instead we're going to again use logarithmic differentiation to get rid of the quotient and the exponent so that we can make it simpler to differentiate. So I want you to try this on your own again. We'll start off with that and then I'll show you how to do it. So pause, do it on your own, and now we're going to go through this. So take the natural log on both sides. And then you can simplify using log properties. Then differentiate. Here I'm going to simplify this fraction out. Let's do that, an example of that. So we'll do 2 over x minus 2 minus x over x squared plus 1. So then this is going to be 2 times x squared plus 1 minus x times x minus 2 over x minus 2 times x squared plus 1, which is 2x squared minus x squared is x squared plus 2x plus 2 divided by x minus 2 times x squared plus 1. Then I'm going to multiply the y on both sides to just get dy dx. And substitute y back in. So y was x minus 2 squared divided by square root x squared plus 1 times all of this stuff. Right, so imagine how complicated these problems were to do when you had to use the quotient rule, right? You'd have so many things going on. This hopefully makes some of that stuff simpler. And then we can do some simplification with this, and we'll get x minus 2 times x squared plus 2x plus 2. I can cancel one of those out. And then this would be x squared plus 1 to the 3 halves. So hopefully that gives you a sense of looking through different ways to take derivatives with these problems. So I'm going to stop this video here.